Now, and as you told, the topic of discussion will be artificial intelligence and machine learning for predictive maintenance. So, the agenda of presentation today, I'll discuss about the brief terminologies of what is AI, what is ML, and what do you mean by maintenance. So then followed by I will speak on maintenance strategies. So we are having a couple of maintenance strategies. We'll see how they are associated with the Industry 4.0. Then we'll see the recent developments in AI/ML technologies which are being applied by various industries for predictive maintenance. We'll also come across key benefits of application of AI/ML in predictive maintenance. We'll see the implementation challenges from ethics point of view, from government norms and policies point of view. We'll also discuss a couple of case studies, and then I will summarize the work with the uh, future trends. What will be the future trends in AIML for predictive maintenance? So, starting the session with the basic definition. So, before I start directly the definition, let just I assume everyone is from mechanical engineering background or industrial engineering background. So we always come across various kinds of conveyor belts in manufacturing on mining plants. Also, we have seen various types of pipe or pipelines, especially in chemical and petrochemical industries. And time to time, all these components require a kind of maintenance. Even in case of breakage, they are supposed to be fixed. So we all know that failure is often no fatality. There is a lack of proactive identification. So when factory equipment fails unexpectedly, usually the production will slow down. And when the production will slow down, time and money will be lost. So when the time and money will be lost, obviously the consumer, the customers' patience will be also compromised. Therefore, maintenance strategies are significant in case of industrial and manufacturing systems. So nowadays we are having so many emergence of newer technologies, especially the generative AI, which will not only predict the machine failure but also it will tell about the remaining useful life of the components. So with this kind of overview, I'm just starting the basics of AIML in predictive maintenance. That is the definition of maintenance you are seeing on your screen. So basically, uh, what is maintenance? The first question arises here. It's nothing but the process of preserving the performance and longevity of the equipment. And we all know that it is nothing but the work done to keep machines working well and prevent them from breaking down. So, time to time, we have to inspect, we have to verify all the spare parts, components of the machines, and we have to repair or replace them accordingly. So, with this definition of maintenance, moving ahead, so everybody is aware about artificial intelligence and the emergence of artificial intelligence nowadays. So, basically, it was a term which was coined by Professor John McCarthy in 1955. And according to Professor McCarthy, AI is the science and engineering of making intelligent machines. So, if we look at the current definition of artificial intelligence, according to National Artificial Intelligence Act of 2020, it says that a machine-based system that can, for a given set of human-defined objectives, make predictions, recommendations, or decisions influencing real or virtual environments. So we know what is AI capable of nowadays. Moving ahead with the machine learning, and as we know that machine learning is a subset of AI, and it is also a kind of way how we are going to use AI or apply AI in our manufacturing environment. It was defined by Arthur Samuel in 1959 as a field of study that gives computers the ability to learn without being programmed. So there is no need of keep on programming every time. Just the machine will adapt itself and it will keep on learning and improving. So the best example in this category we can see across the various LLMs nowadays, that is ChatGPT, Gemini AI, and DeepSeek. There are so many LLMs which are like we are just submitting the data and they are upgrading themselves by their own. So as today's topic of discussion is about predictive maintenance, we should know about different maintenance strategies. So moving ahead with that, so various maintenance strategy, if you classify them in a broad manner, so usually we are having two types, that is reactive and proactive. So reactive is nothing but whenever there is a breakdown, immediately we are fixing based on the situation. Like if the machine or the component is really vital, then obviously we have to go for the immediate fixing. Otherwise we can ignore it. The best example in reactive we can keep in a day-to-day life is replacing a bulb in our homes. So we replace the component only when there is a need or there is a failure in the component. So with this reactive kind of strategy, now we are moving further with the proactive. So proactive involves a group of planned and predefined activities, and these planned and predefined activities are performed on the system to prevent failures. And in this category, we can give the example of servicing our two-wheeler or four-wheeler for their clutch, brakes, and oil changes and all. And also one proactive activity you can involve here, that is wearing helmet while driving two-wheeler, riding two-wheeler, or buckling off your seat belt when you are doing air travel or you are riding a car. So further proactive strategies can be classified in two categories: preventive and planned, and predictive. So our topic of discussion today is predictive. Now this is a broad classification, but if you keep the manufacturing sector into mind, we are going to classify the maintenance strategies in four categories. They are reactive, planned, proactive, and predictive. So if we look at all these categories, each time we are leveling up for all these uh, maintenance strategies. So reactive is a very basic strategy, whereas if you move ahead, planned, proactive, and predictive, they are leveling up each time when we are going and maintaining the equipment or machines for our manufacturing system. So basically, we know about the most basic approach, that is reactive, and it is also known as run to failure maintenance. And it means one can only act after the machine has breakdown. It is also known as the cheapest approach in short term, but if you consider for the long term run, reactive approach will be costly. It's a costly affair actually. If you talk about the planned maintenance, it involves performing maintenance on a regular basis, regardless of machine conditions. Sometimes, you know what happens, because of the time frame, we have to go for the servicing of our vehicle or servicing of our, machines. Sometimes, though that part is not, fully utilized, we have to replace because of the time bound, because of the, planned activities. So sometimes we see that the useful part which are not fully utilized are getting replaced uh, without their optimum utilization. So examples in this category, you can keep changing you know oil of the car after every 8 to 10,000 kilometers. So that can be one of the real time example for planned activities. If you talk about the proactive, so proactive is a like it's a level up strategic approach, and it involves analyzing the root cause of the failure. So here we are going to see the major concern why the system is getting failed, and accordingly we are going to make the changes to avoid future failure. So it this proactive maintenance strategy may involve redesigning the system sometimes, or also we can change the way we are operating the machine, so that will identified based on only when you are doing the root cause analysis. Moving further with the predictive maintenance, that is the you know topic of discussion today. So predictive maintenance is the most advanced and data-driven form of maintenance. This maintenance uses cutting edge analyst and sensor data for predicting the future failure for the system. So that is what predictive maintenance is about. You can see the definition on your screen here. So it is a data-driven maintenance strategy that uses AI/ML and IoT, especially sensors and all, to predict the failure before they occur, or you can say the future forecasting of the machine failure. So usually for predictive maintenance, we are moving from time-based servicing to the condition-based servicing. So based on the condition and the prediction, we are going to replace the components or we are going to service the machine. So this is a comparison of our entire, you know, maintenance strategy. So you can see here the philosophy for reactive, planned, proactive, and predictive. So the philosophy for reactive will be fixed it whenever it breaks. Planned will be fixed it on a schedule. So as I already explained all these terminologies, so I'm not going to repeat the entire PPT here because the brief introduction I have given in my previous slide. So what I will do, I will just summarize it through the real-time example. So reactive, as already I told you, that changing a light bulb after it burns out or it gets fused. Whereas the planned activity will be nothing but a kind of changing the car's oil every 5,000 miles or approximately 8,000 to 10,000 kilometers in our Indian context. Proactive will be a kind of you are already using some tools and technologies to avoid the failure. So wearing helmet while riding two-wheeler, that is will be a kind of proactive maintenance strategy. Otherwise, we all know about the uses of voltage regulator, especially in our home for our home appliances to avoid any kind of fluctuation and to safeguard our home appliances. Whereas the predictive maintenance, the best example you can cite here, the analyzing vibrations in the machine so that we can predict the future when the machine is going to break down. So with this brief discussion, we are getting so many questions actually. So like so many questions, few questions I have lined up. So these questions will be like, what are the main components of AI-based PDM system? So predictive maintenance, in short, we call it as PDM. So what are the state-of-art PDM methods in context of AI/ML? So we'll see the popular strategies. It is really difficult to summarize all those strategies in a 1 hour of schedule, but I have picked up few popular methods which are being applied by various companies. What are the advantages of AI-based PDM techniques over traditional techniques? So we'll see that also, and the challenges and limitation. So these total five questions will be answered in this discussion now. So now we are moving to the main part of this discussion, that is AI/ML technologies in PDM. So the first thing we have to look at, what is the role of AI in our PDM. So if you look at this slide, artificial intelligence in PDM is used to analyze the machines, and when we are analyzing the machines, we are how we are analyzing, we are getting data from the sensors and the transducers, whatever the devices, IoT devices we have used for our machine. So these systems will provide you know a kind of data, and those data will be analyzed, and based on the analyzation of those data, we are going to find out the future failure time of the machine. Also, we from that data we can also see, is there any kind of fluctuation in the behavior of the machine, that is known as anomaly detection. And also we are going to calculate remaining useful life. So overall, AI supports real-time decision making in industrial settings. So there will be two scenarios. One scenario will be like you are gathering data from the history and feeding up to the machine. That is a kind of learning environment, which will come further. I'll discuss. That is known as supervised learning environment. And second one is like you are analyzing the behavior of the machine in real time and gathering the data, uh, and then you are seeing, is there any fluctuation in the behavior of the machine happening or not, and that is known as anomaly detection. So we will see all these things. So machine learning in PDM. So there are total three strategies with respect to the machine learning. As I told you, one will be the supervised learning. So for that, we must have some historical data related to our machine, and that historical data will be fed to the machine learning algorithm that will analyze, and based on that, it will detect the machine behavior. Similarly, we are having unsupervised, machine learning. So this unsupervised machine learning is a kind of real-time data analyzation, and it just keep on its eyes on the behavior of the machine, and if there will be any kind of anomalies, it will immediately alert to the operator. So it will have a kind of real-time data, and if there will be any deviation from that real-time data, it will inform to the operator of the machine. So we are having the most advanced ML in PDM, that is known as reinforcement learning, and it will not only use the historical data but also the real-time data, and it will keep on updating itself and provide you the optimized maintenance strategy for like better maintenance in a shorter period of time. So that is a kind of reinforcement learning. So you can see a kind of typical workflow which are supposed to be used in any PDM system. So that is nothing but the sensors, data collection, AI/ML algorithm, predictions, and maintenance action. So sensors, nothing but we are having different categories of sensors. Like those sensors are more usually mounted on the machines, and from there we are going to note down the or generate the data. So that data can be in terms of temperature, pressure. Sometimes if you talk about the warm or welding environment, so it will be current, voltage, and even the gas flow rate. So all such data will be collected using sensors and other IoT devices. So usually that data which will be collected here, either it can be you know saved on the uh, cloud, that is nothing but the central server. Cloud is nothing but a kind of central server, or sometimes it can be sent to the you know the edge, nothing but the local host. Nothing directly, you can say in a layman's language, you can consider is the machine itself. So edge and cloud computing comes into the picture here. So the data will be saved either on cloud, or it will be directly sent to the local host, that is edge. So on this data, we are going to apply, AI/ML algorithms, and those AI/ML algorithms will be, analyzing the data and making some predictions, whether we have to replace the component or we have to replace the entire machine. So based on the prediction, we are going to take the action accordingly. So usually there will be a kind of interaction between the machine and the operator, or the person who is taking care of the maintenance of the machine. So there also, that will be the next topic of this discussion, that is human machine interaction, and the prediction and maintenance action for any manufacturing environment will bring the picture of human machine interaction. So with this flow of predictive maintenance system, we should know what are the key elements. What are the key elements for our predictive maintenance using AI/ML? So if you look at the key components or key elements of a PDM system, which is based on AI/ML, so few components you can see they are like repetitive, like sensors. So I have already explained these sensors just now. Data pre-processing. So data pre-processing, if you look at data pre-processing, is very significant. One of the significant studies uh, in AI/ML prediction, which is used for predictive maintenance. So whatever the data we are generating from sensors, that data is raw data, and it will always have a kind of noise and some inconsistencies. So therefore, what we have to do, we have to pre-process the data so that we can remove all such consistencies and noises. Otherwise there will be accurate prediction will be missing. So therefore we have to process the data, we have to clean it, we have to normalize it, and sometimes there will be a couple of data missing. So based on the large set of data, we can also predict that missing data. So at second stage, we are doing data pre-processing, and in pre-processing, we are removing all the abnormalities in the data. Then this high quality data is being fed to the AI algorithms. So AI algorithms, not only it uses machine learning, but nowadays there is a lot of advancements. So that will use deep learning technologies also. And this AI algorithm using ML and DL are nothing but the brain of the PDM system. These modules are responsible for determining when maintenance actions are needed, and they can recommend preventive or corrective maintenance tasks. Also, they can recommend for scheduled maintenance, or sometimes they will just trigger whenever there is a need for maintenance or replacement of the component in manufacturing environment. Then we are having decision making modules. So the insights and predictions generated by AI algorithms are processed by decision making modules. These modules are responsible for determining when maintenance actions are needed. So these modules will recommend preventive or corrective actions based on the recommendation they are getting from the AI algorithms. Now, all this data has been processed, and some corrective actions have been recommended. But how we are going to interact? So for that, we must have communication and integration. So communication and integration will ensure the data or the insights which are generated by the systems are translated into action. This component, this communication and integration component, involves interaction with various stakeholders, especially the person who is operating the machine. Also, sometimes the management, because management will be making the decision whether to replace or not. Furthermore, if you look at the integration with the ERP system, because ERP system will play a significant role to take care of the operations of the machine. So therefore, we need this communication and integration. Then only we can, you know, apply, or we can look at the predictions made by the machine. Last component is the user interface and reporting. So to make all these insights accessible to the maintenance staff, there must be some user interface. So everybody, like what we are doing on computer right now, that is a kind of user interface. Therefore, we are able to interact. The mobile handset we use. So everything which is in a virtual world must have some user interface to interact with the human entity. So therefore, user interface and reporting is really significant. Otherwise, how the maintenance staff will know which strategy and or which kind of replacement or changes we have to incorporate in the machine. So in addition to this, we are also having advanced AI methods, and those advanced AI methods are nothing but are used to obtain resilient, reliable, secure and highly stable results, and that is your integration of various things. So that will be sensor data and IoT integration. So that is really significant. You might have experienced one case study where you have installed your AC. So the you I don't know how many of you have experienced the E06 error. So E06 error in AC, inlet unit and outlet unit, is nothing but a kind of you know recommendation for the maintenance. So their sensors are not able to connect with each other, means sensors are not fully integrated. So therefore you may get that E06 error in your split AC. So that integration is really significant to for full utilization and functioning of the system. So data integration is also significant. So data integration will combine data from various sources, including historical maintenance records, real-time sensors data, and other external factors like weather conditions and all. So all these weather condition external factors will play significant role. So because in manufacturing environment, if there will be of too much lubrication, or if there will be lack of lubrication, so that condition external condition will be also going to impact the machine functioning. So therefore data integration is significant here. Then we are having digital twins. So digital twins are nothing but a kind of virtual environment. So whatever the things we are going to do in the real time, before applying those things in real time, we are going to create a virtual environment, and we are going to run the kind of simulations. The best example I can cite here of you know Boeing aeroplanes. So what they usually do, I was attending one conference in Bangalore. So their India head of Boeing was there, and he just shared his experience. Like every time to reach the optimum efficiency of the machine, or the best machine or best aeroplane to be made, we can't keep on making the regular models and testifying. So there will be lots of scrap, time consumption, you know the overall cost of the manufacturing an aeroplane will increase. So what is the solution for that? So they are going to run the entire aeroplane simulation in a virtual world, and there we are going to create all those external factors, on the weather conditions, and based on that they are going to testify their model. And when they are going to get success in the model's testification, then only they are going for the manufacturing of the real aeroplanes. So but still, coming to the recent tragedies which are associated with Boeing, we still know that Boeing is a kind of controversial company nowadays. So just to make you aware what is digital twin, so I cited this example. So usually we are going to create virtual replica of physical asset, and then we are going for the testification before bringing the whole system into the real world. Next one is agent cloud computing. Already I told you about agent cloud computing. Edge is nothing but a kind of local host that can be directly your machine, and cloud computing can be your you know server, which will be connected to your entire machine system or manufacturing unit. So here is the one of the main content of this discussion: different types of popular AI ML algorithms which are being used in the predictive maintenance. So you can see I have figured out a few important algorithms here, and those algorithms are uh, used by so many researchers and so many organizations uh, for predictive maintenance in their manufacturing system. So if you look at the first one, that is a regression model. So usually regression models, uh, they create a relationship between the sensor data, nothing but the features, and the target, nothing but the machine, whether the machine is going to be failed or machine needs again any kind of repair. So that regression models will create a relationship between the input system and the output system. So the best example you can cite here for regression model, that is nothing but a prediction of wear rate of cutting tool in CNC machining, and that will be used by analyzing the data of spindle vibration and also the cutting force. So for that we are having dynamometer and all we are using, and other setups in CNC machining system. So that will provide us the real time data, and based on that we can predict the wear rate of the cutting tool. Also, we can cite another example of logistic regression used to estimate probability of pump failure based on temperature and vibrations thresholds. So these are few examples of regression models. And why it is important, like, because regression models are very simple. Even we whenever we talk about optimization and all, we always and in not always but in the most of the cases we use regression models because they are really simple, they are easy to interpret, and they are very quick to apply. So because of that we are preferring regression models. If you look at the second strategy, that is random forest, also known as ensemble learning. So it uses multiple decision trees to capture complex nonlinear relationships in the failure data. The best example you can cite here for this is bearing life in rotating machineries. So bearing life in rotating machineries, by how you are going to analyze that? By combining temperature, vibration, and acoustic features. So whatever the temperature, vibrations, and acoustic data we are getting from our sensors, based on that we are going to predict the bearing life of a rotating machinery. Similarly, we are going to detect abnormal patterns in compressors and turbines using ensemble learning model. And why it is important? Because no, this model is robust against noise. If there will be any kind of noise, if you remember, I talked about the noise and all in data pre-processing. If there will be any kind of noise, so that model will take care of all those things. It will also handle high dimensional sensor data. So regression sometimes will not able to handle so much of data, real time data, but ensemble learning will easily handle high dimensional sensor data. Therefore, we are going to use this method for analyzing the bearing life for any rotating machinery. We are having the third one, that is SVM. SVM, and SVM is a nothing but SVM is nothing but we are going to find a decision boundary between healthy and faulty states in high dimensional data. And for this, you can give the example as the fault detection in gearbox. We can also uh, see the example of fault detection in hydraulic presses. And why it is so important? Because it is a very useful method to know the anomaly detection in any kind of machining environment. Next one is the neural network and deep learning, that is CNN and LSTM. So CNN stands for convolutional neural networks, and LSTM is nothing but the uh, long short term short term method or modeling, you can say. These are the two deep learning or kind of advanced machine learning techniques. And Usually they are used for complex machine signal analysis. The examples you can cite here is thermal imaging of motors, and also vibration based remaining useful life forecasting of any machine tool or any machine system. Why they are so important? Because they capture non-linear patterns in large data set. So we will have too much of data set like real time data, and they will able to catch, will there be any a kind of disturbance in the entire data set. If there will be any kind of disturbance or any kind of anomaly, they will able to easily catch that, and they will notify the operator. Similarly, we are having auto encoders, key means clustering, and reinforcement learning. So I'm just uh, focusing on reinforcement learning. That is really important, and that is one of the most advanced technique, and it will optimize maintenance schedule dynamically. Usually, in reinforcement learning, it has one agent, and that learns the best course of action. So agent will, it acts as an agent, and it learns best course of action, and based on the activities, it will perform the maintenance task. That sometimes that can be through trial and error, and also sometimes can be rewards or penalties. The overall goal for reinforcement learning will be to maximize the overall uptime and efficiency of the system. So, example you can understand, reinforcement learning model is tasked with managing the maintenance schedule for multiple machines. So the model gets a reward for keeping a machine running. So reward is nothing but when the machine keeps on running, that will be reward, and penalty is nothing but a kind of machine failure. It also gets a cost for performing unnecessary maintenance. So sometimes, if you remember the types of manufacturing strategies, there we came across time bound replacement of or maintenance of the machine. So that reinforcement learning will keep the knowledge of the cost which are being used for unnecessary maintenance, and over the time the model learns the optimal time to schedule maintenance for each machine, balancing the risk of failure against the cost of maintenance. So it will give you a balanced approach, because it will analyze the the machine spare parts, and it will also analyze whether the spare parts are fully utilized or not. If they will be utilized fully, then it will recommend for the replacement. Otherwise, it will suggest that you keep on using the component, the spare parts, for RUL, remaining useful life will be predicted. So, what are the key takeaways from the entire, AIML, popular AIML techniques, what we have seen so far? So, if you look at the traditional machine learning techniques, they are like nothing but the regression, SBM, and uh, RF. So, they are usually good for structured sensor data. So, you will have a labeled data, then only you are able to apply traditional ML. Means there will be no noise in the data, there will be no kind of disturbance or missing data. So that in that sense we can apply traditional machine learning techniques, whereas the deep learning techniques like CNN, LSTM, and autoencoders, so they are going to analyze the real time data, and it is not necessary for them to analyze the structured data only. They can based on any unstructured or unlabeled data, they can predict the environment, whether we have to go for the maintenance or not. Then we are having reinforcement learning that, as I already mentioned, it will optimize the cost-driven scheduling in real-world factories. Nothing but unnecessarily changes of parts, which will, improve the manufacturing cost of the entire system, will not be recommended, because it will analyze the entire, scenario, and based on that only, it will, trigger the maintenance activity. The question arises, like, why all these things we have to come across, like why do we need AI powered predictive maintenance data? So if you look at the main reasons why do we need. So whenever we talk about the need for any new things, so usually in that scenario we compare with the traditional or existing methods. So if you look at the maintenance approaches, the reactive is nothing but the fixed the component only after failure. So if you take the example of any manufacturing environment, if you are going to wait for the failure and then after failure you are fixing the entire manufacturing system, as I told you in the very beginning, like time and money will be lost and also the patience of the customers. So for a long run, it is not recommended. So therefore, it has been written here: costly downtime and safety risk. Safety risk means if there will be all of a sudden failure of any machine component, so operator may get harmed in that scenario. So if you look at the preventive is also a kind of time based. So the examples which I cited for them is like servicing of your two wheeler or four wheeler. So what you are doing here, because of the time bound maintenance, uh, without any optimum utilization of the resource, you are going to replace the components. So that is what unnecessary part replacement, and that will lead to the higher cost at the end. So there, AI comes into the picture, which will learn the data, from the history and also from the real time, and based on that it will detect hidden patterns and anomalies, nothing but the deviation beyond human and manual analysis. So that anomalies are really difficult for us to identify, but application of AI will easily find out the hidden patterns and disturbances or any kind of unusual activity in the data. And based on that, it will keep on improving and learning itself and keep on recommending what is best for our manufacturing system. So benefits of AI powered PDM. So based on this, we are having certain benefits. So you can see there is a data from Oracle which says that if we are using AI based PDM, there will be a reduction of up to 50% of downtime. Means we can avoid a machine failure, and when we can avoid machine failure because all the things are interlinked. So when we can avoid machine failure means we are able to produce the components, the parts on time. We are able to supply all those things to the consumers on time. So there will be also the continuation of the supply chain, which is also one of the benefits of AI powered pdm. So also the cost optimization will be there when you are able to predict the failure. So there will be on time. So there will be a reduction of 10 to 40% of maintenance cost, because already we are aware about when the the component will fail, and just before the failure we are going to replace and we are going to maintain, or we are going to uh, take care of the entire system accordingly, and that will overall optimize the cost of the production system as well as the maintenance system. Also, asset life extension. So as I told you that AI will be capable of calculating or estimating a remaining useful life. In short, we call it as RUL. And when we are knowing that what will be the remaining useful life of the component or of the machine system, we can easily prevent secondary damages. Also, the overall operational efficiency will be improved. If you look at the safety and compliances, so according to International Standard Organization and also the OSHA, nothing but the kind of organization which talks about the safety of the factory workers and the people who are working in any you know manufacturing sector. So if we are using AI powered PDM, that will also take care of safety, and it will also follow all the compliances, and rules and regulations. of the various international organizations. So the question next is why now? Like, why do we need now? So why we're doing AI based PDM now? Because we are having so many advanced tools and techniques. So if you look at in terms of data generation, we must have sensors and IoT. So all these sensors and IoT nowadays we are having abundant you know uh, in our system, and also high quality. All these sensors are available in the market. So there is a explosion of IoT sensors, and also there is a continuation of the data. Like we are having lots of past history, and even that history can be used to train our AI ML models. Also nowadays, the cloud and edge computing is affordable. Like you might have heard of Google Cloud, like server and all, and they are having uh, not so costly, the plans to so that you can save or secure your data in the cloud. So these days, all these things became very, affordable. So therefore, we are opting for AI powered predictive maintenance. Also, if you talk about the algorithms, so we are having so many advanced algorithms. So especially, I can cite a few algorithms in terms of optimization from one Indian, author or researcher. I think everybody is aware about RV Rao from SBNIT Surat. So he, like, even I have used his algorithms like Rao 1, Rao 2, Rao 3 algorithms. Even there are TLBO, Jaya. So there are so many algorithms, which were made by Professor R.V. Rao from SBNIT Surat, and those are being used in real-time manufacturing environment to know the optimal efficiency of the manufacturing systems. So, what is the key takeaway from this slide? So, if you look at AI-powered PDM creates smarter, safer, and cost-effective operations across mechanical system. So, if it is not there, somewhere we are you know not able to cope up with the market trend, and if you are not able to cope up with the market trend, it's obvious you have to compromise on so many things. Ultimately your you know productivity will be hampered. That will lead to the hampering of your supply chain, and if there will be a lead to the hampering of supply chain, it's obvious you will not gain profit. So AI powered predictive maintenance is the need of the time. So if you look at the application of various AI ML techniques from a time frame 2018 to 2023, so I have gathered this data from research paper. So how researchers are using? So you can see the pattern here, the number of various AI methods according to Web of Science in between 2018 to 2023. How many papers people are publishing? So all these are the famous techniques. A few of the famous techniques we have seen, like SVN, autoencoders, LSTM, CNN. We have seen their mechanical, applications and why they are important. Similarly, we are having a few data from our Google Scholar and how the pattern and the publication trends which are running nowadays using various AI/ML techniques with respect to the predictive maintenance. So for this, I followed one of the papers which you can see on your screen. In in line with that, we are having recent advantages in PDM system. So what are these recent advantages? Nothing but they are combining uh, two or more than two systems, and they are coming up with the advanced techniques. So if you look at like PDM plus AI, if you look at the first column, every column will have PDM plus AI. PDM plus AI means these are the two systems which are fixed, but in accordance with these two systems, we are also having the third addition. So in the first case, we are having digital twin. So already I explained you about the digital twin, nothing but uh, the virtual world, virtual reality, you can say. So its recent advantages are talking about the hybrid kind of predictive maintenance system where we are not only using the AI but also the emerging technologies like digital twin, IoT, edge and cloud computing, and augmented reality, virtual reality, and mixed reality, and we are improving our predictive maintenance system for better productivity, for better utility in society. So these are like the various for advancement which I came across several research papers, and you can have a look on this slide, and if you are having any question on this, please ask. There is a kind of uh, little bit pause here so that you can analyze these things and you can ask any question on this. So I don't. Is there any question, Suresh? Suresh, Balaji, do you have any question? If there is no question, then I'll move forward. So if you look at the previous slide was about the application of you know uh, single kind of single AI techniques or single AI ML algorithms. Now this slide shows you about the combination of advanced techniques AI ML like PDM plus AI plus digital twin, PDM plus AI plus IoT. So these are the patterns which I have observed, like how people are publishing articles and what are the current trends. Similarly, this data is from Google Scholar, so you can see uh, there is a lot of publication pattern using digital twin and AI, also IoT and AI, and the publication pattern using cloud computing, edge computing, and AI is still growing, and that will be a kind of uh, upcoming recommendation or future scope. There we can apply all these techniques in our manufacturing environment, and also meanwhile as we all are kind of researchers, so we can write some articles on these techniques. Similarly, it applies for augmented reality, virtual reality, and mixed reality. So, augmented reality, virtual reality, mixed reality, nothing but a kind of we are training the models using you know uh, images, a kind of computer vision and all, and accordingly they are recommending us the decision whether to replace or whether to discard the whole system or not. So overall, what do you think, which one will be the better? So if you look at the comparison is done on three parameters: accuracy, effectiveness, and scalability. So if you compare only AI based means the single technique like CNN, LSTM, regression, random forest, RF. So if you compare the only AI based techniques with traditional one, in terms of accuracy, it's obvious that we are going to get more accuracy in case of AI based techniques. Also, the cost effectiveness in terms of long term runs, traditional will have high cost because traditional methods is nothing but the reactive. Means when there will be failure, we are going to replace the component. So for long term run, it will be very high cost. Whereas if you look at the scalability, so AI based can will be able to handle too much of data as compared to the traditional method. Now, if you compare only in between AI, so machine learning is like a kind of basic AI, things, and deep learning is the advanced AI algorithms. So if you compare between them, which one will be the better? So you can easily see that deep learning is going to surpass machine learning in terms of accuracy and scalability easily. What are the key implementation challenges for AI based predictive maintenance? So if you look at especially the data quality and reliability, so though we are having advanced IoT system nowadays, we still have a kind of doubt on the data we are getting. So there is a trust issue because uh, that data will have some kind of noise. Also sometimes there will be the missing things, like how you can say, like you are interacting with any kind of LLM like chat GPT, Gemini, and all these things, and when you are uh, asking some output, I am not sure that in one shot or in one go you are getting the exact output what you are expecting. So there is a kind of trust issue in case of data quality and reliability. Also the data integration. So data integration across various platforms, it is really challenging task because we are having different types of machines. We are having different types of their spare parts. Also the protocols in different countries, or in different organizations, are not standard. So when there is not so standard, like a kind of uh, global standards, if everybody is following global standards, then the data integration will be easy. Like for example, data integration, you can, in a layman's language, you can understand the the temperature data will be in the centigrade, pressure data will be in bar. So we have to like how you are going to integrate all these things. Like in India, we measure distance in kilometers. In other European countries, they prefer miles and all. So again, there will be integration of data across various nations. So that is also kind of uh, issue. Like in a one two data, or in a very small set of data, that is not a big problem. But when you are analyzing huge data set, obviously data integration is an issue. Also the leveling issue, lack of historical failure data. So all this, the record of the previous data is also a significant role it is playing, because all the organizations, I don't know like how many organizations are having the record of the previous data of around 50 years or 10 years. So the existence of such data is also I know crucial, because that data will be used for supervised machine learning models. See, if that data is unavailable, then it will be difficult for any manufacturing system to implement supervised machine learning models. Apart from that, we are having technical challenges. So that model generalization, if you look at AI models, often tuned to specific equipment and hard to scale across plants. So like our models are specific to the particular domain. It cannot be generalized one. So that is also a kind of technical problem. Also the trade-off between edge and cloud computing. So there we came across very technical terms like latency, bandwidth, and real-time constraints. Also the cyber security risk, which is really crucial nowadays, and therefore there is emergence of this field. And we might have seen the separate cyber security branches in our institutions. So that is also a kind of challenge, technical challenge, like securing our data. If you look at organizational challenges, so skill gap. So as all these technologies like AI, ML, and all these things are like they are recent advancement. Like the more application we are seeing, especially in Indian context, from past 5 years or 5 to 7 years. So we still lack of expert or the trained or skilled people in this domain. Also, it's a human tendency that we always uh, resist the change. So the operators, like who are taking care of their traditional machines, they will be finding really difficult, or they just hesitate themselves uh, to adopt all these changes. That is also kind of challenge. And it's obvious when you are implementing all this AI based predictive maintenance system, then it will attract high initial cost, because you have to spend a lot for sensors and IT infrastructure. Also, you have to hire skilled operators for operating all these things. Also, there will be regulatory and compliance issues. So uh, you have to follow the government norms and industry standards across the nation as well as across the globe. So that is also kind of challenge here. So what is the key output of this slide? So the challenges like AI powered PDM require high quality data, scalable infrastructure, and skilled workforce, along with the trust. So trust issue, like the data we are getting is really trustworthy or not, that is also one of the key challenge in implementation of AI ML based predictive maintenance system. So this is a small case study. So here what this case study is talking about. Uh, there is a very large manufacturer company in Europe, and they are supposed to make ball bearing. And ball bearing, like, it requires precision manufacturing, because they are being utilized in motors, turbines, pumps, conveyor, like almost in all high end mechanical equipments. And the company which is producing this, they were only looking for reactive maintenance. So they are following the traditional maintenance strategy, that is reactive maintenance. And that was leading to a kind of uh, failure or pause of their production facilities time to time. So they consulted one company that is not an Alton. You can see the source at the bottom, Alton company, and they are the French multinational company. Even they are having their branches in India too. And they proposed the solution for this problem. They applied AI ML based PDM approach, and they suggested to replace the reactive maintenance to the predictive maintenance by incorporating the newer technologies. So for that, they use sensors. They gathered all the data, vibration, acoustic, temperature, and all, and they used advanced deep learning methods, and also went for useful life prediction of the machine components. So we know the application of ball bearing and all. So what was like, by doing that, they were able to not only minimize the runtime by 50%, almost 50%, but also they were able to reduce the scrap around 2%. So 2% scrap reduction is a huge in terms of manufacturing system. So for more details, you can just follow this, like the Alton, the source which I have mentioned here. This is a key takeaway. So AI powered PDM for ball bearing shifts maintenance from failure driven to intelligent driven. Nothing but the reactive maintenance to the predictive maintenance, ensuring uptime, cost saving, and safety. So uptime means the breakdown were reduced. Cost saving means they were able to reduce the scrap by 2%, and also there, as there were no sudden failure, so safety of the workers were also taken care of. There are so many examples. A few more examples you can see on your screen here, which I have taken from Oracle. And the famous company, you everybody is aware about, GE Aviation. So you can see here, like, even you can also use the maintenance of welding robots, uh, in especially in automobile sector. So you can see, like, by implementing AI based predictive maintenance system, the company was able to reduce 70% of inspection time, as also they were able to improve the quality, welding quality by 10%, because they were able to identify the faulty spare parts, and they were those parts were replaced on time. For that, the company used uh, computer vision and deep learning techniques, so that they can easily inspect the welding robots and all. Another example here, it is about the G aviation, and you can see the benefits after implementing. They were able to boost engine reliability. Also, the maintenance cost of the airline were significantly reduced, and the safety, which is really, after Ahmedabad incident, is a prime concern in aviation sector. So they were able to enhance the operational efficiency of the aviation sector or their aeroplanes. So what are the future trends? So we are talking only about the artificial intelligence, machine learning, and all. So in future, we have to take care of the you know XAI, that is known as explainable AI, and also the trustworthy data sets that will be playing a significant role. So there we will have the generative artificial intelligence along with, in line with, deep learning and machine learning. And plus, there must be a kind of human interaction with all these, the data sets, what the historical data or the real time data sets what we are generating. And there will be a significant role of big data analytics, digital twin, because digital twin will not only give you the uh, a kind of virtual testification of the models, but also it will going to reduce the overall scrap. Also, as I mentioned about AR, VR, MR, and all these things like IoT, uh, integrated Internet of Things, and cobots, nothing but the collaborative robots. So all these are like advancement which we look into for the future adaptation of uh, in predictive maintenance or manufacturing sector. So overall, if you look at the nutshell, so we are if you are able to uh, incorporate all these things together, we are going to build a kind of smart factories. So nowadays we are talking about smart manufacturing, smart factories. So that will be the future trends in terms of AI ML based predictive maintenance. That is what I have mentioned over here in terms of. So these are few references which I followed for preparation of this talk. If you are having any question, I'll be glad to answer. So these are a kind of brief overview. It's obvious you can't keep on discussing the entire AIML techniques here within short duration. It was just, my prime focus was to give you a kind of overview about these things, how the system, what are the key components, how the system works, how uh, which techniques are used where, in which scenario, with some case studies. So that's all from my end. If you are having any question, I'm open to the question.
So, dear participants, if you have any query, you can ask in the chat box. Shall we
Otherwise,
be?
we are having second one more session. There, I'll be sharing my email ID and all, so you can you
Sure,
know
sir. Sure, sir. There will be no issue,
you
sir.
can drop me
So
any
we,
kind of message or any kind of query, or even I think many of us are researcher. Even I'm open to
yes, sir.
collaboration and all in any kind of manufacturing
Sure, sir.
related articles.
Sure,
So
sir.
any question?
Right now we are not having any questions, sir. So we will be having 5 minute break, sir. Is it okay?
Can we start at just 10:20? I need 10 minutes of time.
Oh, sure, sir. Sure, sir. No issue.
Okay. So at
Okay.
10:20 we'll meet, and then I will discuss the next things. Okay.
Oh, okay, sir. Okay, sir. Thank
Thank
you,
you.
sir.
Hello, shall we start?
Yes, sir.
Yeah,
We can
just
start. Yes, sir.
let me share the screen. Is it visible?
Yes, sir. It,
Mm, yeah. So, good morning once again. So, now in second session, I'm just going to give you an overview on human robot interaction in Industry 4.0 environments. So, for this, I will just introduce the topic and then I will take for this I will introduce the topic and then I will take a real time case study which we have done, me and my PhD scholar. So usually he has done the most of the things. So let's see. Let's start the session. So in this we are going to discuss about the introduction of uh, the topic, and then we'll see the experimentation. I will also discuss about the optimization, and if time will permit, then I will discuss about the characterization, and otherwise we'll go with the summary and future work. So basically, I'm starting the topic human-machine interaction in terms of a case study, which I have taken from WAM. Everybody is knowing about WAM. That is wire arc additive manufacturing, and we know it is a metal print 3D printing technology. I mean, not only metal, but it has been applied earlier. When it came, it was applied to the you know different type of materials, and but we are working on metal 3D printing technology. And in this, everybody is, as we know, that everybody is aware about. In this, there will be the uses of any welding technique along with the robots for deposition of the material or metal layer by layer, and that will enable the fabrication of large and complex metal structure. So usually this warm method bridges traditional welding with advanced additive manufacturing technique. And within Industry 4.0, warm has become a cyber physical process. Cyber physical process means uh, you have to insert some drawings. So that is what a kind of cyber process, like you are inserting the data, and physical process based on that data, the machine is making the print, or machine is manufacturing the component. That is physical process. Therefore, we are calling it as a cyber physical process. So human, you know, robot interaction is really crucial because WOM is not fully automated. So because you have to insert the data, you have to take care of the controlling of the path, whether it is like time to time monitoring, it is required. So therefore, we are like having the requirement or need for human expertise plus robotic execution. So for insertion or data input, we need human expertise, and for execution of task like for manufacturing of large and complex structures, we need robots. So basically, that execution will be done in terms of design and path planning. So, like one category you can cite here as CNC machining. Also, like we are able to make integrate parts like so complex structures can be easily machined. Similarly, like collaborative deposition is there, and then process monitoring like condition monitoring is also happening, because robot not only it will deposit the material, but also in the integration with IoT it will able to monitor the entire process. That is also known as a kind of condition monitoring, and it will let you know whether the tools or the spare parts are in a well condition or not, as what we have discussed in the predictive maintenance in the previous discussion. And accordingly, if it will be feasible for the system to make automatic correction. It will correct, otherwise it will notify uh, through one user interface to the user or the operator, and accordingly we have to take the corrective action. That is what where the human robot interaction is becoming really crucial, not only for the data insertion but also for the execution, monitoring, for any kind of fault detection, and modification of that fault, or any kind of implementation of changes in the system. So here, what I have taken the case study of regulated metal deposition welding, that is the playing the role of welding feature along with the robots. That is what layer by layer deposition. So before directly jumping to the data, just I would like to tell about the RMD welding technique, and it was introduced by Miller in 2004, and it is a fully automatically controlled short circuiting process. Circuiting means it's a kind of gas metal arc welding process, and in that we know there are total three types of processes, sub processes. One is the short circuiting methods. Second one is the deep modular transfer method. Third one is the um, uh, you know global modular transfer method. So it is a short circuiting category, and it is an advancement over existing gas metal arc welding process. It not only monitors and controls the welding current electronically, but also it controls the entire process. So you can see it consists of total uh, seven processes or seven stages. So I'm not going to explain all these things because this is not the part of discussion today. But just to give you the a kind of overview how the wavelength are being formed in RMD welding process. Just I kept this figure. So for more details, you can just follow the source which I mentioned over here. Regulator metal deposition welding technique for welding applications by Javora and Rashesh Patel. So you can just go through that link and you will get the whole description. There are various, processes, advantages, application, everything they have mentioned beautifully in this chapter in this source file. But we have to know the comparison how RMD is better than other existing categories for the particular application where this RMD technique is being applied. So if you look at the SMAW and TIG, nothing but the gas tungsten arc welding process. So RMD is much better than this because the travel speed is almost double of them. Training time, as it is fully automatically controlled process, so training it does not require much training for any kind of operator or welding personnel. There will be no spattering and also a kind of slag generation. Means the rework, the post rework is not required because spattering will be almost negligible, which sputtering is a kind of drawback in especially in high temperature welding, or especially in case of gas metal arc welding process, so that there will be no sputtering and all in case of RMD welding. Also TIG is also a kind of low welding process, there will be no sputtering in TIG also, but overall if you'll compare, there will be no sputtering, no slag generation, no fume generation, which is also kind of environmental feature or quality for RMD welding. And because of that, there will be no need for any kind of post weld or rework. If we talk about the repositioning or changing, the position of the pipe or a kind of any kind of workpiece, the repositioning of the workpiece is not required in RMD. So if there will be so much of complicated shape, then only we can go for the repositioning or changing the location of the workpiece where the welding is supposed to be done. That is advancement of RMD over other welding techniques. So in this case, we have taken the base material as low alloy steel, which is also known as chromium molybdenum low alloy steel or chrome moly steel. These are the elements we can see here on your screen. The elements like it consists of iron, carbon, and all chrome. Basically, it is like how it is different from others because of the composition of chromium and molybdenum. So the properties you can see, the mechanical properties of the base material. the ultimate tensile strength, yield strength, rupture strength. All this data you can get on any internet, uh, source. So these are the base material, and the selection of parameter here we have done based on their application, as well as the property of the material. So there must be a compatibility between the base material and also uh, the electrode wire, whatever the wire you are going to deposit on the machine. So there must be a compatibility. Otherwise, you are not going to get the strength, the property, what you are looking for after the deposition of the uh, electrode layer by layer on the base material. So based on the property of the material as well as the application of the material, we have selected some parameters. So before selection of parameters, we have defined some objectives like what we are going to find out, what are our the objective of our work. So we have first objective we have kept here to analyze the effect of various variables like current, voltage, and gas flow rate on the bead geometry and morphology. So mainly how the deposition is going to impact the heat affected zone, depth of penetration, bead width, and bead height of the base material. So that is the parameter, the output responses, and on those output responses, what will be the effect of the input variables like current, voltage, and gas flow rate. Then we have applied a couple of techniques, optimization techniques. If you remember in previous discussion, I talked about RAW 1, RAW 2, RAW 3. So that application we have implemented here. So why we have implemented? Because we want to know the optimized warm parameters, so that we can create a real time, uh, component or real time samples for the further testification. And third one is to know the microstructural and mechanical characteristics of the prepared samples. So these are the warm variables which I have selected: welding current, welding voltage, and gas flow rate. So base material, as I already mentioned, it is a chrome moly steel. The standard terminologies will be ASTM A387 grade 11 class 2 material. Even you can find this terminology in terms of AISI also. But anyway, you can follow any one standard, that is up to you. So we have taken total 5 levels for each of the parameters. Like current has been varied between 90 to 130. Similarly, voltage we have varied in between 13 to 17, and gas flow rate, that is a liter per minute, that has been varied in the range of 13 to 21. So for this three input parameters and 5 levels, I have applied Taguchi orthogonal array technique, and which will give you the total 25 sets of experiments which are there on the screen. So total 25 experimentations according to this table have been performed, and those all experiments have been performed on a Miller Continuum 500 welding machine, which this machinery is available at two places. So that is Miller Welding Group is there in Vadodara. So if anyone is willing to do any kind of experimentation, they may visit their site. They are having really good welding setup and all. And another, like, it is available at one of the universities in Gujarat, that is Pandit Dindayal Energy University. So you may collaborate and contact their labs for experimentation and all. My scholars are working at Pandit Dindayal Energy University for experimentation and all. So these were the trials which what we have taken here using worm, and all the samples were cut on Maxman semi-automatic horizontal band saw machine. So we have prepared the samples, and you can see the cut pieces here. And those cut pieces were actually like the bead on plate trials, and they were then polished etched and water rinsing. For polishing, we have followed the standard polishing procedure, like emery papers were used, and then no belt polishing was done, and then etching was done using nitrile, because nitrile was well compatible. 2% nitrile we have used here, and white nitrile is quite compatible with low alloy steel. And immediately we went for the water rinsing, because if you'll keep nitrile for a long time, it will start uh, corroding the material. So we kept the each sample, and each and water is sampled under the microscope for macroscopic examination, and from there we have noted down four output responses. Those are heat affected zone, depth of penetration, width, and with height. So like this is one texture of how all those output responses were measured. So you can see the bead width, which is horizontal straight line, the longest line here in the diagram. Bead height, the emerged portion. Depth of penetration, the just below the bead width, that is depth of penetration. How uh, up to what level the penetration has been done. And apart from the penetration, there will be definitely a kind of heat affected zone, so that is HAG. So this is the entire data we have collected for all the 25 experimentation. And uh, after that we went for ANOVA to know the effect of each uh, kind of the to know the effect of input parameters on each output response. So if you look at the first table itself, ANOVA for heat affected zone. So if you look at here, as per the data, what we have analyzed, voltage is playing significant role for heat affected zone. Similarly, for depth of penetration, again, voltage is playing a significant role. For bead width and bead height, also voltage is playing the significant role, and that the entire data has been plotted here in terms of diagram. So overall, if you look at the contribution, the voltage is the significant input parameters, and followed by you can see the current and then gas flow rate. So that is what the contribution of each input variable for one output response. So input variable for for HAG, 52% effect is of voltage. Then current is having 19.11% of effect. So that calculation you can do using ANOVA technique, and that data you can just simply put in any tool for graph generation. It will give you the such plots. So next we have went for the optimization. In that here we have followed three optimization techniques. One is a very basic one, that is Topsis Taguchi approach. Then next one I will be discussing about PCA, principal component analysis. That is a kind of moderate and middle technique, you can say. And the advanced technique for optimization, we have used RAW 1, RAW 2, RAW 3. So we'll see one by one. So this is the proposed model, and this is the standard steps what we have followed. So uh, initially we have selected the input variables and their levels, parameter selection, everything was done. Then output response was generated. So after generating output response, only we are going to create the decision matrix. So that decision matrix, you know uh, as per the Topsis model, we have to normalize the decision matrix. So there may be some questions like all the data is in how, like, what is the need for normalization? But in this scenario, like data, all the data is in obviously you can go for direct use, but there will be some like other output response, for example, which is having different kind of output unit. Then in that scenario, like for example pressure, just hypothetically I'm saying the pressure is having different unit. Then how you will create a decision matrix, because all the units are not same. So therefore it is recommended in the Topsis method that we have to go for the normalization of the data. So after normalization there will be allotment of weights to the each of the output response. Like which output response is getting higher preference. So the sum of all the weights must be 1. You cannot exceed 1. So usually for this case, we have given the equal preference to all the output responses. Like there will be some questions like if you are giving some more importance to one output response, so why you are biased towards that particular output response. So to make the data unbiased, we have kept equal weightage to all the output responses. Then we have calculated the positive ideal, the best, and negative ideal, the worst solution. So it's a kind of iteration here starts, and after iteration starts, we start calculating the distance measurement for all those responses from the ideal solution. So we'll see through the data in the coming slides. Then there will be a determination of overall performance coefficient, and that will be supposed to be the nearest to the ideal solution. And then further we can again apply Taguchi for signal to noise ratio analysis. So all these like steps which have been followed in proposed model. So this is the first one, the normalization, data normalization. So this is the formula which you can see here on the screen can be applied for data normalization. So normalized data for all the output responses has been calculated. It's a very easy step. You can just simply put the data in Excel and you can calculate. Anybody can calculate. That is not so big process. And if you are not able to find out, please contact me. I'll explain, or I will collaborate with you for explanation of all this. So formation of weighted normalized matrix. So here we are giving the uh, like weight to each of the output response. So whatever the normalized data we are having, so each normalized data is given some weight. So W value here I have given equal like so 0.25 to all these normalized data. So 0.25 for HAG, 0.25 for DOP, and 0.25 for remaining width and with height. So all the output responses have been given equal weightage. So the based on the existing literature, we have to identify so which output response should be better in which condition. For example, depth of penetration. If we talk about the welding or warm, depth of penetration plays a really significant role. So therefore, it should be as high as maximum. Similarly, if you talk about the heat affected zone, it should be as low as possible. So that is what you are seeing on your screen. LB criteria. HAG, for HAG bead width and bead height, it should be lower is better criteria. Whereas for DOP, it should be higher is better criteria. And these are the formulas which have been used. And based on that, we have calculated positive ideal, anything of the best and the worst solution. So that A negative is like worst and A positive is the best solution for each of the output response. Then we have calculated the separation distance and closeness coefficient. For that, we have used uh, the formulas like SI plus, SI minus, and for closeness coefficient, we have used the formula CI plus. So for this, like after implementing this formula on the positive ideal and negative ideal, we have formulated a new set of data in terms of separation distance and closeness coefficient. And also we can see the last column, second last two columns. Here itself, I have applied Taguchi's signal to noise ratio. That is what uh, the fourth column is showing here. And also we have predicted the result whether the Taguchi SN ratio, which has been calculated here, that is in line with the prediction as per the Minitab. So we have used Minitab for all these calculations. So if you look at the mean response table and all, so that is also generated from Minitab after insertion of the data there. So from there, from mean response table, we can easily see welding current is playing significant role, as and followed by, sorry, welding voltage is playing significant role, followed by welding current and gas flow rate. And this is what the main effect plot. Again, you will get the same diagram from Minitab. And if you are having the license of this diagram, it is recommended to use a direct. Otherwise make it a new diagram using any tool. Otherwise, nowadays you might have seen papers are being detracted if your institution or you do not have the license of that particular software. So be cautious while using all this data. If you are having license, well and good. Therefore, you can see on the screen that current voltage and gas flow rate. Uh, these diagrams are made by our own team. We have not used direct diagram from the Minitab because we do not have the license. Sorry, but I mean for running of the data and all, you can use the trial version or the the other versions which are available on internet. So on recorded line, I can't say all these things, but just be cautious. If you are having license, then only use all this data in your paper or in your thesis. Otherwise, remake the diagram. The second method we have followed here, that is principal component analysis, Taguchi approach. Why Taguchi? Because everywhere we have used signal to noise ratio uh, or prediction of our the output response, the data we have, whatever the data we have obtained here. This is again proposed model or principal component analysis. So you can see almost steps are initial steps are similar. The data normalization and all. Third, if you look at the third stage, data normalizing and check for correlation. So till here everything will be similar. Then application of PCA, principal component analysis, evaluation of major principal components. So then again in that we are having two different approaches. One is the composite principal component known as CPC, and second one is the uh, quality quality loss. So we are going to apply the both of the branches of you can say sub branches of principal component analysis. So again, the similar kind of things we are seeing like what you have seen in the previous, you know, Topsys Taguchi approach. The lower is better criteria for heat effector zone, bead width, and bead height, and higher better criteria for depth of penetration. So that is what normalization data will look like. Then we are searching for the correlation coefficient, and for that the best technique is to use Pearson correlation coefficient. And this is a formula again. This is not so typical. You can get so many already made Excel sheets on internet, and you can feed up the data from there. They will the entire, like, the program sheet will calculate and it will give you the correlation coefficient. So if you look at the correlation coefficient between height effector zone and depth of penetration, the remark is really significant. And it's really significant because heat affected zone and depth of penetration will evaluate your entire warm strength, like the layer by layer deposition you have done, that will be analyzed. If you look at the heat affected zone and bid width, that is not so significant. Similarly, depth of penetration and bid width is not so significant. So all this, like, which correlation is significant and which correlation non-significant, can be easily calculated using Pearson coefficient. Then, like, you might have seen eigenvalue, eigenvector in mathematics. So like we are going to calculate eigenvalue, eigenvector. Why we are calculating? Because you want to eliminate response correlation, which are not so significant. So for this, we have calculated. If you look at the principal component PC1, PC2, PC3, they are like taking the majority of stakes, like 58%, 27.6%, and 7.9% of data variation. Whereas PC4 is a very low accountability, so we can neglect it actually, because till for PC1, PC2, PC3, like, what is PC1, PC2, like the interaction. We have PC1, PC2, PC3, so all these interaction we are calculating here. So for the major three itself, we are having 7.4% of share. So with this assumption only, we are moving forward. We are neglecting the remaining, or we are just uh, like 2.6%. We are calling it not so significant. So calculation of CPC, here actually I have created a hyperlink how the step by calculation will be done. If anyone will be in the need, I can share all those sheets personally. He or she can mail me. I'll share all the calculation. I'll share the step-by-step calculation, which I have created a hyperlink for that. So how it is, the calculation will look like. You can see here, like we are calculating the significant, principal components. PC is nothing but a principal component for all the 25 experiments, and based on that, we are composite principal component. We are composite principal component we are creating by using the formula and all, and then with respect to that, we are also estimating the signal to noise ratio. Similarly, for composite quality loss, we are doing the same thing, and accordingly, we are calculating the signal to noise ratio. So, if you look at ANOVA for composite principal component, like sub 1 category in PCA, so for this, when we are applying ANOVA, we are seeing that voltage is playing significant role with 67%, followed by current, that is 22%, and then gas flow rate. Also, there will be a little bit of error because we are not, using the entire 100% of data, because we are already neglecting a little bit of data which is not so significant. So there will be little bit of error. Similarly, for complete quality loss, we are seeing the same. Means from both of the methods, we are able to predict that voltage is playing significant role, followed by current and then gas flow rate. This is what the main effect plot for both of the sub methods CPC and CQL. Similarly, the third method, that is RAW algorithms. So actually, RAW algorithms uh, consist of total three sub algorithms, that is known as RAW 1, RAW 2, and RAW 3. So I mean, the naming itself is like Rao 1, Rao 2, Rao 3. Professor Avi Rao has not given any specific name, just he kept his surname and added 1, 2, and 3 because it's a combination of total three algorithms, and this is the optimization route how Rao 1, Rao 2, Rao 3 algorithms are being implemented. So again, you know everything will start with the decision matrix, and from there you have to apply raw algorithms. How it will be applied, let's see then. So what is raw algorithm? The overview, as I told you, Professor Avi Rao has proposed three metaphor-less algorithm. Metaphor-less means there will be not so many complications in the data. They are like based on the population-based method actually, and sample size and iteration, it is like it is taking care of the specific sample size. So we are having sample size of only 25 experiments, and based on that we are going for the iterations and all. So there is no need for any algorithm specific control parameters. Like if you remember in genetic algorithm and all, we are having algorithm specific control parameters. So all these control parameters are not required because it is a metaphorless algorithm. These are the three algorithms, uh, nothing but the mathematical model for them. You can see on the on your screen. So this is what the development of relation among variables, all the variables like output responses and R square, so correlation coefficient. So you can see the uh, coefficient, uh, the R values in table. So for these correlation coefficients are really useful for prediction of or the validation of the output. Output result. Like you higher the value means your prediction or your calculation or your optimization is up to the mark. So you can see here higher value of R square is desired, and which is there in the table. So and again we will calculate with the uh, calculate the R square using these formulas, like for all those Z1, Z2, Z3, Z4 you are seeing on the screen, and the adjusted R square. So you can see like both of the values are very close to each other, and means there will be a little bit of error because, as I mentioned, we are not going to, because we are neglecting little bit of noise or kind of non-significant data. This is what the relative error which has been calculated. So usually, it is recommended that a relative error should not exceed 10%. Even in some cases, it should be less than 5%. So if you look at the values, our relative errors are in line with the standard data, like up to 10% for HAG, 9% for DOP, and for width and width height, it is 5 and 8% respectively. So we are going to calculate one normalized combined objective functions. For that, this is a formula, and this formula again, you can follow the articles of Professor R.V. Rao. So this is the how the entire data will be combined into one function. So there are so many methods, but as I'm using Arvirov sir's algorithm, so I followed his function, like the function combined function he has suggested in one of his articles. So the nomenclature and all you can just read it out. Uh, just have a little bit of pause and you can read it out. And if you have any question or here, you can ask. Meanwhile, so moving further, so this is the convergence plot, which will like you will feed the data if anyone is having a good idea about MATLAB and MATLAB programming and all. So you will get all these diagrams from MATLAB. So convergence plot, like you can't make all these plots in uh, anywhere in on any tool, but even nowadays, because of the emergence of technologies, you can use Python programming and even Anaconda and all you can use to generate all these convergence plots. So, but these are these plots were obtained from MATLAB. So also we have done the comparison of all uh, you know uh, algorithms proposed by Professor R.V. Rao. So TLBO, that is known as Teaching Learning Based Optimization Method, J algorithm, or RAW 1, RAW 2, RAW 3. So all RAW algorithms proposed by Professor R.V. Rao were compared, and we have seen RAW algorithms are perform, performing much better than TLBO and J algorithms. So if you look with this concluding remarks, if you look at because time is not permitting for microstructural discussion and all. So we have conducted ANOVA test. We have also created like mean response table, and for ANOVA test, from ANOVA test we can say that voltage is playing more significant role. From mean response table again, we are in line with the our previous prediction of ANOVA, that is again voltage is playing significant role, and from all these optimization techniques like Topsys Taguchi, PCA Taguchi, and Rao algorithms, we are able to find out the optimized welding parameter, that is voltage as 100 ampere and current is 100 ampere, voltage as 13 volt, and gas flow rate as 21 liter per minute. So so usually, this is the optimized, warm parameters, and these optimized warm parameters, using this setting, we can next stage is like we can go for the, real time material deposition at this specified setting or specific setting, and then we can conduct the mechanical characterization or other metallurgical characterization, like we can go for the tensile test, impact test, even we can check the hardness, and followed by how like the tensile test breakage and all is being justified. For that we can do the microstructural characterization. So there we can go opt for the a kind of optical microscope as well as scanning electron microscope. Going with TEM is really difficult because again preparing the sample of to that level is tedious. So That's all from my end today. Few references and references again. I have created. There are lots of references. So I have created a hyperlink for that. So with this, I'm open to any question regarding uh, the both of the topics again, like uh, application of AI ML in predictive maintenance and human robot interaction in Industry 4.0. So WOM is actually Industry 4.0, a case of Industry 4.0, and there we are using welding technique in line with the robots. So here I have used the case of RMD welding technique, which is the advanced welding technique with robots for layer by layer deposition. And the work is still under process, and we are planning for the further, microstructural characterization. So even anyone who want to explore the field can opt for another welding technique like TIG or any other advanced welding technique. Like nowadays, people are using cold metal transfer also, CMT warm method. Uh, but as already so many works are done on CMT warm, we opted for RMD warm. Still, it is like a kind of unexplored field in this domain. So, and for all this, data interaction, obviously we need user interface. We need somewhere to communicate with the robot. So for that, we are having IoT system and sensors and all, even the programming and all. We are AIML techniques. We are uh, applying on a couple of techniques we have seen in our previous discussion. So that's all from my end. If open for any question. If you are not having any question, that is also okay. You can ask me personally on my WhatsApp or through email.
Sir, we have two queries. You can see on chat box also.
Yeah. See, there is one question. It's a great lecture, sir. How can you deal with the problem of overfitting
Sir,
in model with the view message? So usually we go for Pareto of uh, technique. Like there we go with the overfitting of the model and all. Pareto plots we plot for the overfitting. And one more question I am seeing here. Just a minute. Uh, what is the need for three different? See, uh, actually, the work can be done using one optimization technique. But uh, if you remember in previous lecture, I spoke about the trustworthiness of the data. So we do not know whether this optimization technique is really giving the same output or optimized parameter or not. And especially in Indian context, uh, we are really having lack of trust in data and all. So so therefore we opted for three different optimization technique, and significantly we observed that all those optimization techniques are giving the same optimized parametric setting. Means we are in line with the optimization techniques what we obtained in uh, first optimization technique, second optimization technique, and third optimization technique. So means overall our data were validated. For that purpose, we are using different optimization techniques. And another question: why same weights have been chosen for the toxins? Yeah, because there will be always a question like why like biased and unbiased weight criteria selection. So to eliminate this question, like whether like people may say like why you are so biased towards one specific parameter or output response. So to eliminate this we are assigning the equal weightage. Now there are so many weight calculation techniques. Actually I did not include because it will increase the length of the discussion. So a few of the techniques you can see like uh, SAW method is there, if I am not wrong. uh, So usually, I'm missing the names because I have not used them. But there are some weight, especially weight calculation methods. So you may borrow the internet. Otherwise, I will just drop your email ID. I will reply you on that because currently I'm not getting all those names. Uh, any other questions? I'm seeing. No, there are only two questions.
Yes, sir. Okay, sir, we can conclude the session.
Just a minute. I'm just querying about the various methods. So methods in for weight calculation. Yeah, I told you the SAW method, simple additive weighing method. That is a quite famous one. Simple additive weighing method. There are so many methods, and depending on the situation, you can opt. So, any other question? No.
No, sir.
Okay. Thank you.
Okay. Thank you very much, sir. Sir, for delivering such an insightful and engaging lecture on AI ML for predictive maintenance and human robot interaction in Industry 4.0 environments. Sorry. Sir, your session provided us with valuable perspective on applications of artificial intelligence and machine learning in smart manufacturing, as well as their role in shaping the future of Industry 4.0. I'm sure the participants have gained a deeper understanding of the subject and will be inspired to explore it further. On the behalf of organizing committee and all the participants, I extended our heartfelt gratitude to you for taking the time to share your expertise with us today, sir. Once again, thank you very much, sir.
Thank you. Thank you.
Thank you, sir.